Okay, here is one area where math crosses over and becomes useful for science class. That is scientific notation. I'll just read this with you. A number written in scientific notation is written in the form m times 10 to the n, where 1 is less than or equal to m, which is less than 10, and n is an integer. Now let's talk about this just a little bit. This number out here, m, it needs to be some value that is between 1 and 10. It's okay if it equals 1 because of the less than or equal to symbol there. It is not okay if it equals 10. If it equals 10, well then you would just call it 1 because it can equal 1, and then just increase the power of 10 that you multiply here, so the exponent for n would actually just be 1 greater if it was 10 instead of 1. Or you would call it 1 instead of 10. Here's kind of an example of when you'd actually use scientific notation. The light travels, I can't even say that number, I'm not even sure how big that is to say million, jillion, cajillion, whatever it is. But light travels that distance in 1 year, and that's in a vacuum. That's a large number. So large, I can't even think to what to call it. Quadrillion, I don't even know. I'm not even going to bother. This distance is called a light year, which is not a measure of time, by the way. It's a measure of distance. It is difficult to write out this number every time you want to use it. An easier way is to use scientific notation. So we'll come back to this maybe later in the video lesson, but let's take a look at some examples. First, we're going to talk about the definition, the word definition. It's just a method for writing large or small numbers using a power of 10. For example, 7 trillion written out in standard notation would be a 7 followed by 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, I went over into the other box. Because it's that cumbersome. I mean, there are just so many zeros to write. It's a pain in the neck. There are too many symbols. In scientific notation, this would be written as 7, because that's my value in this number that's between 1 and 10. I wouldn't want to say 70 times something or 700 times something. I want a value that's between 1 and 10 every time I do scientific notation. So I'm going to say then times, and this is like one of the only instances where we use that multiply x anymore. Otherwise, we would just use a dot or parentheses or something to say multiply. But in scientific notation, we do still use this x symbol for the multiply, which really we shouldn't have used this since elementary school. Anyway, 7 times 10 to some power. Now, what is the power? Well, it depends on how many times the decimal needs to be moved from standard notation to get it into scientific so that we've got a number that's between 1 and 10. Well, in standard notation, the decimal point is right there. And so that means that I've got to move it over. Well, if it's right there, 3 times to that comma, 6 times to this comma, 9 times to this comma, 12 times to get it to that comma, which is where it stops for the standard notation, or the scientific notation. It stops just before the 7. So let's then say times 10 to the 12, because that's how many decimal places we moved it. Okay, 402. This one's a little bit easier to write. It's not that long of a number. In fact, it's actually going to be more symbols to write this in scientific notation, but that's okay. We're just practicing our scientific notation skills. 402 could be written as 4.02. Now that is a number between 1 and 10. Here's my multiply x times, and how many places did I have to move that over? Well, this time it had to move from the just right of the 2 so that it's just right at the 4, and that was 2 decimal places, so that's a positive 2 as the exponent on the 10. Here are some more examples, and this one is going to actually give us an example of a negative exponent. Notice that this number here is much, much larger than 1. This number here is much smaller than 1. This one, the second one, is going to have a negative exponent on it, whereas the first one is going to have a positive exponent on it. That negative exponent, just as a reminder, is something that was smaller than 1 versus the positive exponent, which is something that's larger than 1. So if we want to express example 1a here in scientific notation, we need to write that as 7.82. Those remaining zeros, I don't need them. unless for some reason in scientific notation or the problem that you're working on says that those are significant digits, which I doubt they were. That 2 is probably the last significant digit. And I'll leave significant digits for your science teacher to explain. But it's going to be 7.82 times 10, and now I need to figure out how many times I need to move the decimal place. Again, since this number is bigger than 1, it's going to be a positive exponent for the 10, and I need to move it over 3 times to get to this comma and 6 times to get to that comma, so times 10 to the 6. This other example, example 1b here, is going to be 4.01, and this one's going to be times 10 to the, well, in this case I need to move the decimal over 1, 2, 3 times in order to get it to be just after the 4 there, so that this number can be between 1 and 10. And since I needed to move it 3 places, I'm going to call that to the negative 3. Again, this is a negative exponent because this number is smaller than 1. Now let's try some where we've got the number in scientific notation. We're going to express it in standard form. 3.89, so times 10 to the 9. This means it's going to be a number much larger than 1. So I'm going to be looking at something like 389 billion or something like that. Knowing that I'm going to be moving my decimal over 2 places to get it to there, that uses up 2 of those 9 times that I've moved it. I'm going to need to insert 7 zeros then in order to get this to be in standard notation. So here are my 7 zeros. 1, 2, 3, 3, 4, 5, 6, 7. So insert some commas there, and that's the number in standard form. This next problem has a negative exponent on the power of 10. That just means that the end result, instead of being much larger than 1, is going to be much smaller than 1. So let's move the decimal over 5 times from where it is. Here's just a little trick. If the exponent here has a 5, I'm going to have 5 zeros, and then my number, 9097. And that includes the 0 that is in front of the decimal. And that actually was 5 moves, 1, 2, 3, 4, 5, to get it to that spot. So that's just my little trick about multiplying by powers of 10. Again, up here in this case there was a 9, and so it moved 2 spots over from the 3 to be right of the 9, and then I needed 7 zeros. So it's kind of the same thing. Okay, here are some where I'm actually comparing two powers, or 2 numbers that are in scientific notation. I can use the commutative property of multiplication because I'm actually multiplying 4 different things times each other. So I'm instead going to start out by multiplying those things together, and then later multiplying those things together. 5.6 times 1.4 on my calculator is 7.84 times 10 to the, well, I can do this in my head. I can use that property that says when I multiply powers with like bases, both of them being tens, I can add the exponents together. So that's times 10 to the negative 9th power. Okay, example B here is 3.2 times 10 squared cubed. So I'm going to use that one property that says I'm going to multiply everything in there, or the exponent of everything inside the parentheses, times that 3. So now I've got 3.2 cubed times 10 squared cubed becomes to the 6th. So 3.2 cubed in my calculator is 32. So this is equal to 32.768, and then times 10 to the 6th. This is not in scientific notation because this number out in front of the times symbol is not smaller than, or is not between 1 and 10. I need to make this be between 1 and 10, so I've got to go 3.2768 times 10 to the 7th. Since this number was larger, I had to make the exponent a 7. Okay, last example where I'm doing a division. 3.5 divided by 1.75 is just the whole number 2, so that simplifies to a 2 times, and then when I use the property that says top exponent minus bottom exponent, well, negative 3 minus negative 5 really is negative 3 plus 5, so that's going to be a times 10 to the positive 2 power, because this would equal the 2 here. And so that's my answer on that one. Here's my answer for B. Here's my answer for A. Remember that in some cases you're going to have to make an adjustment to the exponent when your power or your number in front of the time symbol does not end up being between 1 and 10. Here are the two problems that I would like for you to have ready for the warm-up for tomorrow. Good luck, students.